Hey everybody. Today we're talking about continuous random variables, which is a sort of random variable that can take values over an entire interval, or union of intervals. By contrast, a discrete random variable takes values only in a non-continuous set, like the integers or something. Some examples of continuous random variables: the length of the tail of a randomly selected dog at the local animal shelter, say in centimeters; the exact temperature at the South Pole at a random moment, say in Celsius; the length of a call to a customer service line, say in seconds. Now, probabilities are harder to describe for continuous random variables than for discrete ones, because there are uncountably many possible outcomes. Take, for instance, that customer service line. A call might last 150 seconds, or 150.1, or 150.01 seconds, or infinitely many other possible values. So, in essence, the probability that a call lasts exactly 150 seconds is zero. And yet, some lengths of calls seem just intuitively more likely than others. And so we should be able to talk about probabilities for continuous random variables in a more meaningful way than just to say that the probabilities are always zero. And we do that by talking about probabilities of ranges of values. So instead of asking about the probability that that call is exactly 150 seconds, we might ask about the probability that it's between 140 and 160. And that's a more meaningful question. One way to visualize a continuous random variable is with a density curve, like the one I'm showing here. This is the density curve for a random variable whose support is between 0 and 4, and as you can tell by looking at the picture, probabilities are lower as you move from left to right. We actually compute probabilities by finding the area under a density curve. So here I'm representing the probability that x is between 1 and 2 in this distribution with that shaded area. You can tell just by looking at it that the probability that x is between 1 and 2 is going to be less than the probability that it's between 0 and 1, for instance, and greater than the probability that it will be between 2 and 3, even though each of those intervals has the same width. Based on the density curve, we can estimate the probability just by estimating that area. So here I have an interval of width 1, and it looks like the average height of that region that I have shaded is about 0.3, so the area is about 0.3. If we know the equation of the density curve, we can compute the exact probability using a definite integral. So let's actually do that. The density curve in the last slide has equation 3/64 x minus 4 squared for x between 0 and 4. So to find the probability that x is between 1 and 2, I integrate that function over that interval. I do a little bit of work, or maybe do this using technology, and I get about 0.297. So my estimate, just visually from looking at the graph a minute ago, wasn't too bad. Any legitimate probability density function, or PDF, has to have two basic properties. First of all, it always has to be positive. These are representing probability densities, so probabilities should always be positive. This property makes sense. Secondly, the total area under the graph of any density function has to be 1. To say that a bit more technically, if we integrate f of x over the support of x, we should always get 1. Now, usually we actually compute probabilities for continuous random variables using a cumulative distribution function, or CDF, rather than using the PDF directly. The CDF is just literally the probability that has accumulated by the specified value x. More technically, probability that the random variable x is less than or equal to the value x. The notation is important here, so make sure you absorb it right now. Little f of x is the PDF, the density function, and it's telling you the height of the density curve. It's not representing a literal probability at x. Big F of x is the CDF, and that's representing the area to the left of x. So that is representing a probability, but not the probability just of one particular x value. Notice that because big F is accumulating probability, accumulating area, it always gets bigger as x gets bigger. The probability density function is the derivative of the cumulative distribution function, and the CDF can be obtained from the PDF with a definite integral, like I'm showing here. The equation on the right, big F of x equals the integral from negative infinity to x f of t dt, uses the dummy variable t that's going to integrate out. So sometimes you'll see this definition with one of the various Greek letters in there, or maybe a u. Also notice that here I've written the integral as starting at negative infinity, and that's because the density function f is always going to be 0 outside of the support. In practice, when the support doesn't extend all the way to negative infinity, like in the last example, we just end up writing the left endpoint of that support for the lower limit of the integral. For instance, using this same example with that same density function as before, we compute the CDF of this random variable by integrating from 0 to x of the density function, just with t's instead of x's. So 3/64 t minus 4 squared dt. When we do out that integral, we get 1/64 x minus 4 to the third plus 1. And I've graphed that function here. Notice that f of 0 is 0, so there we're at the left end of the support, so no probability has accumulated. The probability that x is less than or equal to 0 is 0. Also notice that f of 4 is 1. Now we're at the right end of the support, so all of the probability has been accumulated at that point. The probability that x is less than or equal to 4 is 100%. The CDF can and often is used to compute probabilities for a random variable, that the random variable falls into any given range. Specifically, the probability that x is between a and b is f of b minus f of a. And this means we don't have to integrate every time we want to compute a new probability. We just use the CDF. So the CDF is actually a lot more useful when computing probabilities most of the time than the PDF. For instance, in this last example, we computed the cumulative probability function. We can find the probability that x is between 2 and 3 just by evaluating big F of x at 3, evaluating at 2, and subtracting. So we're just plugging and chugging at that point, not doing any integrals. We get a little under 8%. Geometrically, this calculation means taking the area to the left of 3, the probability to the left of 3, and subtracting out the area to the left of 2, the probability to the left of 2. Now, since the probability that any individual value occurs is 0, we don't have to worry about whether our inequalities inside of the probability statement are strict or not. So the probability that x is exactly between a and b, non-inclusive, is exactly the same as the probability that x is between a and b, inclusive, same as the probability if we include just one of the endpoints. Now, this is not the case with discrete random variables. This is an important place where discrete and continuous random variables really are substantially different from one another. One more example. Find the constant c that makes the following function a legitimate probability density function. Compute the CDF and use it to find the probability that x is between 0.5 and 1. So this is a good place to pause the video, work this out on your own before seeing my solution. So in order for this to be a legitimate probability density function, it has to integrate to 1 when we integrate over the support. So I'm going to integrate that from 0 to infinity. This is an improper integral, so I do it with a limit, and I use integration by parts. I won't talk too much about this calculus here. The result ends up being c over 4. And since 1 equals c over 4, c has to equal 4. So if we want to find the CDF, we plug in the PDF, which is 4 times t, e to the negative 2t, because c is 4, and we integrate that from 0 to x. So here, the PDF that I've plugged in is using t instead of x, that dummy variable. Basically, we want to reserve the letter x for that limit of integration so that our CDF actually has an x in it and not a t. When we do out that work, we get that the CDF is 1 minus e to the negative 2x minus 2x e to the negative 2x. And I won't talk about that algebra at all. The last thing we have to do is to compute the probability that x is between 0.5 and 1. And so we're going to plug in 1 into this CDF, plug in 0.5 to this CDF, and then subtract. Here's the actual math. We end up getting about 33%.